Hi, this is Dr. M.C. Venkata Subbaiah, working as Associate Professor and Head of the Civil Engineering Department. So, present I am explaining unsymmetrical bending. In strength of materials, the unsymmetrical bending is the very important concept to understand the bending of beams. So before going to the unsymmetrical bending, so first of all, so we have to know the term symmetrical. Symmetrical bending. Okay. So symmetrical bending is nothing but, so in case of symmetrical sections, the symmetrical sections are either rectangle or circular section or symmetrical I section comes under the concept of symmetrical bending. So why it is symmetrical is nothing but, suppose this is the x-axis of the symmetrical sections and this is y-axis. Horizontal axis is nothing but x and vertical axis is nothing but the y-axis. Now, so symmetrical is nothing but, so if you see along a horizontal axis, that is xx, so the section here, the section covered here is same below the neutral axis and above the neutral axis, as well as about y-axis. With respect to y-axis, the section on right hand side and left hand side is also same. So see, in rectangular section or the circular section is also same, and in case of I section is also same. So it is symmetrical about either above or below or either left or right of the section. So symmetrical section is nothing but with respect to any axis, that is about xx or yy, the section is same. So this is comes under the symmetrical sections. So then, so coming to the next important one is suppose if you take a beam are having length L. So this is the length of the beam. So the beam is having the length L. So this is the neutral axis of the beam and this is longitudinal axis. Longitudinal axis. So in strength of materials, the longitudinal axis we call it as this is principal centroidal axis. Principal centroidal axis. So along principal centroidal axis, the load condition is very important. So symmetrical bending is nothing but, so for the beam of length L, the load acting on the beam is either it is normal or perpendicular to the principal centroidal axis. So this is nothing but plane of loading. Okay. So now I am taking one section here. I am drawing the section separately. So it looks like say a rectangle. So now this is the neutral axis of the beam and this is vertical axis. Now symmetrical bending will occur due to the load acting on the beam throughout the y-axis is, this is the plane of loading, is truly vertical. So here the load acting with respect to neutral axis is either normal or perpendicular. So the direction here is perpendicular. So this is comes under the symmetrical bending. So symmetrical sections are either it is a rectangle, circle or symmetrical section. So why it is symmetrical bending? The plane of loading acting along the principal centroidal axis is truly normal or perpendicular. So now, so when the this type of symmetrical bending will come across in civil engineering is, so the best examples is here. So if simply supported beam carrying uniformly distributed load and simply supported beam carrying central point load. Central point load. So the best example here is the bridge girders carrying uniform traffic load is comes under the symmetrical bending case. This is the best example. So this is comes under the symmetrical bending. So now I am going to the unsymmetrical case. So now what is meant by unsymmetrical or unsymmetrical bending? So before going to the unsymmetrical bending, so what are the different types of unsymmetrical sections is? Unsymmetrical sections. So unsymmetrical sections are, we know already. So with respect to one axis, the section covered is not same. So this is vertical axis and this is horizontal axis. So this is one type of L section or channel section. The channel section is in the form of shape like C. Okay, so this is vertical axis of the section and this is horizontal axis of the section. So these are the best examples for unsymmetrical sections. So here if you see below the x-axis, here the section is covered only flange, but if you see in the above x-axis there is no flange here, and also left of y-axis, so this is y-axis, the section covered is only web, but whereas on right of y-axis there is no web. If you see in this case, channel case also, the left of y-axis there is the portion of web and there is a portion of flanges, but whereas in right side only the flange portions are covered but there is no web sections. Okay, so like in below x-axis also the section covered is flange and web, the above x-axis also the section covered is flange and web. So suppose if the load is acting in this direction, suppose, so the bending will be more in this side and very less in this side. So that's why the section we consider as a unsymmetrical cases or unsymmetrical sections. Now unsymmetrical bending is nothing but so now I am drawing beam so beam of length L, beam of length L. So we know already, so this is the centroidal axis is neutral axis of the beam and this is longitudinal axis. In symmetrical bending also I am written already, this is principal centroidal axis. Principal centroidal axis. So in the principal centroidal axis, the load acting on the beam is, it is not vertical. So here the load acting on the beam is, it is inclined direction. So if you take one section here, let us say this is XX. So along section XX, it looks like one rectangular case. So this is now the neutral axis of the beam and this is the vertical axis. So in this case, so this is the vertical position. So now in unsymmetrical bending, the load acting on the beam is, it is inclined direction. So this is the case, inclined direction. So that's why it is a unsymmetrical bending. So when the unsymmetrical bending come across in civil engineering is, and this is very, very important. So in case of cranes, the load acting on the cranes to the foot, that is to the wheels, it is unsymmetrical case. Then the another case is angle sections in case of roof trusses. So angle sections in case of roof trusses is comes under, suppose if you take a steel structure, we know already the steel structure is a type of framed structure, framed one. This is the frame. So in this case, so the inclined beams on the framed structure. So here the load conditions here is inclined. So at this point of contact, and it transfer the load into vertical. So this is the unsymmetrical case. So the unsymmetrical bending is very important in civil engineering. So without unsymmetrical bending, the design of steel structures are very difficult. So the next important concept here is, so already we know what is the symmetrical sections and symmetrical bending is. I given the few examples also, and then unsymmetrical sections and unsymmetrical bending. So I given the few examples for unsymmetrical bending also. So then the next concept, very important concept here is stresses. We need the stresses, stress distribution in stress distribution in unsymmetrical bending. So this is the foremost concept in unsymmetrical bending case. So to understand unsymmetrical bending due to stresses, so actually, so initially we had to take the section having with the different shapes, that is nothing but the shape without having any perfect section. For easy understanding, so here I am drawing one circle. The circle is nothing but we have to consider a, this is a one body. So now I am drawing coordinate axis, that is xx, and another coordinate axis is yy. Another coordinate axis is yy. So here xx and yy are the coordinate axis. Now these coordinate axes are meeting at this point. Let us say this is center of gravity. Center of gravity of this section or this body. Next, the next important point here is we are considering the moment acting on the body along y axis. So here m is nothing but the moment acting along the axis y. Then, so to simulate the principal loading conditions, we have to consider the principal axis, that is u and v. So let us take one principal axis passing through center of gravity. Let us say, so this is the principal axis named as uu, makes an angle theta with the xx axis. Let us say this is angle theta. So here angle theta is made between principal axis uu with the coordinate axis xx. Likewise, so we have to take the another principal axis, that is vv, to simulate the loading conditions here. Again I am drawing another principal axis, that is vv, makes an angle theta with the vertical axis y. So this is the second step. So initially I am drawing here xx axis and y coordinate axis. The next step we have to draw principal axis uu, makes an angle theta with the horizontal axis. Likewise, draw another principal axis, that is vv, passing through center of gravity. makes an angle theta with the vertical axis y. Then the next important step is, so we have to calculate the component of the forces due to this moment. Component of forces this moment. So how we resolve the components along VV and UU axis here is, so this is very important one. So now I am separating this triangle separately. See here, I am drawing this triangle separately. So here taking the angle here is theta, and then so this is moment is acting along the axis YY, and this the opposite here is, so this is the side, this side you have to take the coordinate is U. Why? Because see, I am taking this arc is in the form of straight line. Okay, so now this arc length is, it is parallel to UU axis, so that's why I am taking the coordinate is U. So likewise I am taking the another coordinate V. So why? Because so for this axis it is makes an angle theta, so that's why I am taking the coordinate axis is V. Okay, so now this is the moment. So first I am taking sin theta. First I am applying sin for this triangle. Okay, so this is, this side is opposite, and this is adjacent side of the triangle, and this is hypotenuse, and this is hypotenuse. What is the sine? Sine is nothing but opposite side by hypotenuse. So here opposite side is nothing but the component is U and hypotenuse is M. So therefore, so what is U? The component of U, that is nothing but M sin theta. M sin theta. So now it is nothing but, so along the principal axis UU, the stress component is M sin theta. So due to the moment M acting along the axis YY. So likewise again I am applying here, I am considering cos. So cos theta is nothing but, you know already from the definitions, cos is nothing but adjacent by hypotenuse. So here adjacent component is V and hypotenuse is M. So therefore, so what is the stress component along VV axis? That is V is equal to M cos theta. So now I am showing here. So what is the stress component acting along VV axis is, it is M cos theta. Okay, so likewise we are going to identifying, so what are the components along UU axis, that is M sin theta, and we identified what is the stress component along VV axis, that is M cos theta. The next step is very important. So on the periphery of the circle, identify one point. So here I am taking the point here is, let us say P. The point P is having the coordinates XX with respect to XX and YY axis, and I am taking the components is UV with respect to axis UU and VV. So now the first step is you have to identify one point on the periphery of the circle. The next step is draw a line which is parallel to the axis YY or vertical axis. So now the line meets the x-axis here. The line meets the x-axis here. The very important step here to identify the neutral axis is, so the neutral axis location here is, I am drawing the neutral axis is, this is the neutral axis of this section, that is NA. Now so draw a line parallel to UE axis. This line meets the vertical, and this component is, let us say UU. Why it is U? The line is parallel to the principal axis U, that's why this component is U. And again, so from here, from this point, draw a line makes an angle 90 degrees. So here angle you have to present 90 with the, by taking compass. Just you place 0 here and draw perpendicular line. So now this component is V. This component is V. So this is very important to identify the next step processor. Okay. So then next important here is to find the stress distribution of the section. For this, so we have to identify the moments in plane YY and moments in plane XX. Okay. So next step is here. I am writing here. The moment in plane UU will bend the beam in VV axis. So the bending stress is given by, this is very important statement. So the bending stress is given by, so we know already the bending stress equation, that is in strength of materials 1. We know the derivation of bending stress also. M by I is equal to sigma by Y. So here sigma is nothing but the bending stress. So I am writing here the equation in terms of sigma. Sigma is equal to M by I into Y. Okay. So to simulate this bending stress, so what is the bending stress? Moment in plane UU is, see here. So what is M? M is nothing but bending moment. So here we are taking bending moment in the plane UU. So what is the bending moment in plane UU? That is M sin theta. M sin theta. So then, so what is I here? I is nothing but the principal moment of inertia. So principal moment of inertia is considering always with respect to neutral axis. So here, so from here to here, the distance here is U, and so we know already. So the principal moment of inertia we had to consider with respect to VV axis. So why? Because so we had to take the distance from here to here. So moment of inertia is always calculating with respect to reference axis, that is VV axis. Then the important here is the next term is Y. What is Y? So Y is nothing but the distance of extreme fiber from the neutral axis. So here from here to here the distance is U. So that is U. So this is how we have to calculate the moment in plane UU. So likewise, so we have to calculate the, so the moment in plane VV will so bend the beam in UU axis. So the bending stress is given by sigma B is equal to, so from the same formula again. So what is M? Moment in plane VV. So the moment in plane VV is M cos theta divided by, so now, so what is I? Principal moment of inertia I have to take with respect to UU axis, that is I UU into, so what is Y? So that is nothing but distance of fiber from the neutral axis, reference axis, that is V. So here is V. So these are the two cases, moment in plane UU, this is the bending stress equation, and this is moment in plane VV, this is the bending stress equation. The next step is, so we have to find the resultant stress, and this is very, very important. So the resultant stress is given by, so we know already the resultant stress is sum of the stresses in UU and VV axis, that is nothing but M sin theta divided by IVV into U plus M cos theta divided by IUU into V. So here the common term is from two equations, M is the common term. So I am taking M as a common here. The next term is sin theta into U divided by IVV plus cos theta into V divided by IUU. So this is the resultant stress. So anyway, we have the two components. With the help of two components, finally we have derived the bending stress, resultant bending stress. The next important is identify the neutral axis. So for identifying neutral axis, see here in this diagram. So in this diagram, we need this location of neutral axis. To locate this neutral axis, so we have to consider the resultant equation as a reference. This is the statement, at the neutral axis, always the resultant bending stress is 0. The resultant bending stress is 0. That is nothing but sigma B is equal to 0. Okay. So in the above bending equation, so here please keep the bending value is 0. Bending stress is 0. So suppose if you consider bending stress is 0, so next I am writing here. Anyway, we are taking the M as a common term. U sin theta divided by IVV plus V cos theta divided by IUU is equal to 0. So on right hand side it is 0 anyway. M is also going to be 0. So I am writing the remaining term U sin theta by IVV plus V cos theta divided by IUU is equal to 0. So for finding neutral axis location, so first I am placing the cos term in the left hand side, that is I am writing cos first, V cos theta by IUU for mathematical simplicity. Then on right hand side I am writing U sin theta divided by IVV. Okay. Then so we have to take the equation in terms of V. Okay. So in terms of V, V is equal to minus of U sin theta divided by IUU into IUU by cos theta. IUU by cos theta. So see here. So V is equal to, so here sin by cos is nothing but tan, and the remaining term will be IUU by IVV into tan theta into U. Tan theta into U. So this is the location of neutral axis for the stresses in unsymmetrical section. So this is the location of neutral axis. So further you simplify this equation in terms of y is equal to mx plus y is equal to mx. So this is the straight line equation, y is equal to mx. So here y is nothing but the coordinate in vertical, nothing but the moment is acting in y direction, and m is nothing but the slope. Okay. So now I am writing in terms of slope equation. So m is equal to minus IUU by IVV into tan theta into U. So this is also the simplified equation. This is very useful in competitive exams also. in terms of straight line form, that is y is equal to mx. So here m is nothing but the slope. So now what is y by x here? So y by x is nothing but here, nothing but moment of inertia with respect to xx and y axis. So this is the case. Okay. So this is the neutral axis location. So and this is very important concepts, useful in unsymmetrical bending in strength of materials or advanced strength of materials. Thank you.